Hi, I'm Cathal O'Brien. I'm going to talk about the ExSeisPIOL. It's an extreme scale seismic library for parallel I/O. I'm from the Irish Centre for High-End Computing in Ireland and LIRO, the Irish Software Research Centre. So just to jump straight in, the kind of parallel I/O challenges that we've seen when we've been working with Tullow Oil are that there are a mixture of I/O patterns within seismic migration software and seismic processing workflows in general. There's like, in the codes, there's consecutive access of traces. That's, consecutively located traces in a SegWi file, as well as non-monotonic access. That's non-contiguous, sometimes duplicates, and it's non-consecutive. Also in the codes, MPI usage is common as well in oil and gas codes, so that's what we focused on with MPI and MPI-IO limits of around 2 gigabytes per call, presenting challenges when you're faced with multiple terabyte files. So you need to make hundreds of calls, where imbalance in the calls can cause a deadlock in the system. Conformance to the SegWi standard, so the code, our work initially targets the SegWi standard. The support is variable in terms of conformance. A lot of locally defined rules are used by geophysicists, so you have to look in the ASCII or EBCDIC header to see what the rules are. The trace data as well can be stored in the obsolete IBM floating point format. The way trace coordinates are stored is unusual, and elevations and other information. So it's difficult to have all of readability, maintainability, scaling performance in codes without significant work because of the multiple issues that I/O faces. So we've been developing the ExSeisPIOL. It's the extreme scale seismic parallel I/O library. It's an easy-to-use, geophysicist-friendly library with C++ and C APIs, with a Python API planned as well. It provides scalability and performance with a very friendly API. And the goal is to also maintain the performance and scalability and reduce maintenance. So the library can reduce code bases considerably. We did work with a Kirchhoff migration code base, time and depth, and reduced it by about 15% using the library. It also has extensive testing, so it has an extensive testing framework using unit integration and system tests. The design of the library is a multi-layer solution where you have three primary layers, and then also two APIs. That's 2 APIs available in C++ and 2 APIs available in C. And the goal is that it's for computational geophysicists and software engineers writing seismic processing software. So I'm just going to go through the layers, the 3 layers one at a time, and explain where they fit in. So on the data layer, it's initially we're targeting MPI-IO, and then we'll be looking at POSIX and other access semantics. The view of the data layer of the data is as untyped blocks of data, which can be arranged consecutively and non-consecutively as well, and distributed throughout the file. So in a single call, you want to read data distributed throughout a file. The next layer is the object layer, and you can see that this object layer is SegWi specific, but then also with new formats as well that we want to investigate. So the purpose of the object layer is to focus on reading specific blocks of like trace headers or trace data, which can be distributed in the file in some fashion. And then we have the file layer, which is focused on extracting the specific metadata like coordinates and elevation, or the trace data itself, and also read from the binary header as well. And it again is file format specific. There's the two APIs that I mentioned as well. So there's a set API, which is implicit I/O. So that's where we focus on the operations that the end user wants to perform, like sorting a file, performing a 4D bin, or whatever it happens to be. And then there's the file API, which is explicit. And what that means is that you read a particular trace from a particular location in memory, or a particular list of traces, or a block of traces at a particular point, or a block of trace headers, or coordinates. So I'm just going to dive straight into an example now as well. So a very simple example of sorting a SegWi file, also using burst buffers as well to show the application of the library. That it's a simple-to-use library, but it also can exploit new hardware like burst buffers. So just to give a rough guide, I guess, of what the SegWi file format looks like in terms of structure. You have this initial header, which contains the ASCII or EBCDIC human-readable text, and also the binary header with information that pertains to every trace in the file. And then you have a series of traces with associated trace coordinates and other parameters, and the trace data. And I've shown 6 traces here just for the example, but in reality, you'll have several million or billion traces. So you can have up to very large files. So in this example of a sort, you have some traces ordered in some way, and then it's reorganized into some other way. So in the library, performing this, you can have a compilable example in 9 lines, where 3 of those lines are relevant and the rest are boilerplate. The first line is it implicitly, behind the scenes, initializes MPI and any other ancillary object used by the PIOL. Then we have a set layer call here, which is creating an object of a set where any input SegWi file that matches this wildcard will be loaded in, and the output will be output to this file when the object is destructed. So there'll be an implicit output. The sort is then called here. And then in this particular case, it's performing an offset inline cross-line sort. You can also specify your own sorts using just passing functions or lambda functions and stuff. But for simplicity, I've just shown a built-in case. The implicit destructor then, when the set object is destroyed, all significant input and output is then performed. And so the input will read from all these input files. You'll have pre-done the sort, and then it'll generate a single output file based on the sort. It'll also automatically deinitialize MPI as well when this object is destroyed, and do any other tidy up that's necessary. So now jumping onto the burst buffer side of things, the ExSeisPIOL provides hardware-specific optimizations. In the current case, we don't actually have to do a lot of hardware-specific optimizations. We just need to disable collective I/O. The DDN IME is a next-generation data storage architecture, so it's a burst buffer, and it sits in between the compute nodes and the parallel file system. It consists of a bank of high-throughput SSDs or other non-volatile memory, and it also has the smart IME software, so that can help to turn non-contiguous write performance into contiguous write performance, so you get a real boost. Just to go into a little bit more detail, so you have a series of applications performing some I/O. The I/O is distributed across various files, and it's highly fragmented on a per node case. It's stored in the, it's written to the IME. The IME stores it in a way that doesn't cause contention, and I'll show in the next slide. And then the IME reorganizes the data and writes it out in an aligned way to the parallel file system at higher efficiency. So I'm just going to focus in on what exactly is happening here a little bit. So if on a particular node you're writing in some pattern, you have some data located in memory, and you're writing it in some pattern to a single file. So I'm just showing a single file like this. And if you're writing in different randomly located sections of memory on the disk, you can cause contention with other nodes, and you also have to perform a read and write operation as well. And if there's contention during a write, it'll be blocking. The IME helps with this by, when you have these chunks that you're writing, they're stored in a single block or equivalent, so that you don't have contention or the read-write. So it provides a big boost. So I'll just jump straight to the big boost. So what we did was we sorted a 400 gigabyte SegWi file. We're working on bigger sorts, but they're still in queues. So we looked at sorting the file using GPFS and using the IME on the same cluster, so a DDN test system. What we found that was the reading performance is 3.2 times quicker on the particular configuration. So there's going to be always a natural benefit as well from having a high SSDs with a higher throughput. When we came to the write performance though, and that's where the smart IME software comes in, we get a 78 times improvement. So we get a big boost from the first one sorting the file. And so the total speed up for the particular example was 2.6. That's accounting for the non-IO related component as well. So in terms of total time, 63% was spent on IO in the GPFS case, and most of that was write. In the IME case, that's 5%. So as I was saying, the DDN IME is more than an SSD bank. It also has a software advantage over GPFS for this application. So in conclusion, the parallel IO library that we've been developing is ready for seismology workflows. It's SegWi compatible. It can use DDN IME hardware for base fields. It's an easy-to-use API that can help increase productivity. It's production ready, but development is ongoing, and it's going to be open sourced in September 2017 as well. Thanks for listening.
It looks very nice. I'm curious, how large tests are you planning on doing? Because I mean, 400 gigabytes makes the numbers. It's easy to achieve those numbers, if you know what I mean, in terms of the speed ups, etc.
What I have queued up at the moment on a system is generating a 20 terabyte file and then doing the test on that 20 terabyte file. It wasn't ready on time.
Okay. Yeah, that would be very interesting. Thank you.
Have you tried with Lustre file system?
Yeah, actually on iCheck we have a Lustre file system. But I mean, I couldn't compare like with like because it would be different nodes. So I was using a system that had both a parallel file system and the IME. On the current system I'm testing with, it does have a Lustre file system, so we'll see what the performance is like.
So for the seismic data, do you store each trace header with the trace data separately?
No, it's stored together according to the SegWi standard. We just follow the standard.
So in other words, if I want to just read the trace headers, I don't need to like search through the traces to read them.
Yeah. So if you export new file formats, so this is SegWi specific. Locating the trace headers with the trace data. There's nothing in the library that prevents another file format from being implemented, and that's what we intend to do. So if you have a workload that benefits from reading the trace headers separately from the trace data, then you can still use the library. Just choose the right file format when you're using it.
Any other questions? Thanks very much.
Cheers.